In this lecture, I am going to discuss FSK interpretation of MSK signal. In MSK, minimum shift keying, there is no phase discontinuity at all. Okay, and that's why this is also called a continuous phase waveform, because the phase is changing continuously over the bit interval. Okay, and there is an improvement if you look at the hierarchy. We started with QPSK. So where we said there are four phase shifts, 0 degree, 180 degree, 90 degree and 180 degree, and then 270. And 270, of course, it is minus 90. And if you take again magnitude of this minus 90 degree, it is again equal to 90 degree. Therefore, at the max we have plus 180 degree or minus 180 degree phase shift will occur in QPSK at every 2 TB bit interval seconds. 2 sub b, let me say 2 seconds, or at every TB seconds, at every t seconds, where t is a symbol interval. This is called a symbol interval, right? Now, so there is no amplitude distortions and amplitude discontinuity, so this all problems are coming. So that's why we went to offset QPSK. In offset QPSK, we have two channels, like in phase channel and quarters phase channel, and the waveforms are offset with respect to each other by half the symbol duration or TB seconds, and the maximum phase shift is plus or minus 90 degree. Again, there is a still little bit amount of phase discontinuity, and that phase discontinuity occurs at bit interval. So that is no undesirable thing. So to overcome that, we went to MSK. So in MSK, again we have plus or minus 90 degree phase shift, but this plus or minus 90 degree phase shift occurs not at the bit interval, but it occurs gradually over the bit interval. Therefore, there is a gradual phase change over the bit interval in this one, right? So, and the magnitude of the phase discontinuity will be smaller in this. Okay, so no phase discontinuity in this MSK digital modulation scheme. Okay, now let us discuss how we can interpret the MSK waveform as a FSK signal. So this is a preliminary and FSK interpretation. Okay, so in fact the name MSK, minimum shift keying, comes from its relationship with the frequency shift keying. So this MSK comes from FSK. This name is coming from FSK, frequency shift keying, because we have seen that in MSK we have two possible frequencies. At each bit interval we have one of two possible frequencies. In the previous lecture, if you notice, at every bit interval we have one of two possible frequencies. Here let me say F1, in the next bit intervals I may have F2. Okay, so this F1 we already know that carrier frequency plus 1 over 4 TB, and this we said F0 minus 1 over 4 TB, right? So I can write like this, or sometimes this is a little more clear. FC, where C indicates carrier frequency in the pass band. Carrier frequency FC plus 1 over 4 TB. This is FC minus 1 over 4 TB. You can think in this way, or you can say F2 is equal to FC minus 1 over 4 TB, and F1 equal to FC. Let me say, I'm sorry, let me delete this. Let's say this is F1 and this is F2 equal to FC plus 1 over 4 TB. Either way you can choose as you like. Now, what is the separation between these two frequencies? See, this is a higher frequency. That is, if you say in the spectrum, if it is FC and you are going up to FC plus 1 by 4 TB, and this side you are going up to FC minus 1 by 4 TB. Now, what is this range? That is called a frequency separation. This is called a frequency separation. What is the separation between these two frequencies, F1 and F2. Let me call this is F2. Yeah, as you like, this is F1. Therefore, the frequency separation between these two frequencies is given by F2 minus F1. That is Fc plus 1 over 4 TB, right, minus Fc minus 1 over 4 TB. And Fc will get cancelled. So the minimum separation, frequency separation between the two frequencies, or the minimum separation which is equal to 1 by 2 TB. Okay, so it can be shown that this is a minimum separation between the two sinusoidal or quasi-sinusoidal waveform, okay, which will be mutually orthogonal. So what I am saying is, you take two sinusoidal waveforms, let's say sine omega 1t and another waveform sine omega 2t. These two waveforms are mutually orthogonal only when the separation between omega 1 and omega 2, the minimum separation between omega 1 and omega 2 is going to be 1 over 2 times TB, where TB is the duration of these sinusoids. That means sine omega 1 lies between the interval of 0 to t TB, and sine omega t also lies between the interval 0 to TB. So that means you have two sinusoids, sine omega 1t and sine omega 2t, and these two signal lost us from 0 to TB, and this also lost us to 0 to TB. And these two signals, and this one, let me call this is F2 of t, and this F1 of t. And F1 of t and F2 of t both are orthogonal, provided the minimum separation between omega 2 minus omega 1 or F2 minus F1 is equal to 1 by 2 TB. If you don't have this minimum separation, then they are not orthogonal. So in order to F1 of t and F2 of t be orthogonal, then the minimum separation between omega 2 and omega 1 or F2 and F1 will be 1 over 2 times TB. So the minimum separation that is required is 1 by 2 TB. So mathematically, how do you say? So sine of omega 1t sine of omega 2t times dt, this is equal to 0, and integrate from 0 to t. Okay, then it is orthogonal 0 to TB, the bit duration 0 to TB, or you can say two cosinusoidal waveform 0 to TB cos of omega 1t times cos of omega 2t times dt. This is also equal to 0, provided if F2 minus F1, at least I should have 1 over 2 times TB, because this signal exists from the duration from 0 to TB, and this signal also exists from 0 to TB. The duration of cos omega 2t is 0 to TB. So, and if these two signals are orthogonal, provided that F2 minus F1, the minimum separation between these two frequencies should be 1 by 2 TB. Otherwise, it will not be orthogonal. If the signals are not orthogonal, then we will see in the demodulation part that it's very difficult to demodulate it. Okay, now suppose we ask ourselves this question. We realize that F2 minus F1 should be a multiple of 1 by 2 TB. That means what I am saying is F2 minus F1 equal to 1 by 2 TB, or some integer multiple of 2 times TB. Either way you can choose it, any one. So this is a minimum possible separation, and that we needed. That is the reason we call this as minimum shift keying. That is why we call it minimum shift keying. So the name comes from because of this reason. Therefore, the generation of orthogonal pair of waveforms in a minimum frequency shift between the two. So that's where the name is derived from. Okay, so it is derived from its similarity to an FSK waveform. Okay, and since the corresponding FSK waveform is orthogonal with a minimum possible shift in the two frequencies, so that is why we call it a minimum shift keying. Okay, now if we have this interpretation of the waveform, this also tells us that we could possibly generate a MSK like a waveform or an MSK waveform, strictly speaking, by directly mapping the incoming zeros and ones on one of two possible frequencies, right? In MSK, what we said, we have two possible frequencies in one bit interval. If I have one, maybe I can have f2 in another bit interval, and in another bit interval I may have f1 or f2. It depends on the bit interval sequences. Okay, so therefore what we are trying to say is, in each bit interval I am having one of two possible frequencies. So instead of going all this process, what the process, we take arbitrary bit stream and divide the arbitrary bit stream into odd bit stream, and this is even bit stream. This odd bit stream you map onto half cosinusoidal pulse shapes, and this you map onto half sinusoidal pulse. This is cos pi t by 2, and here sin pi t by 2t, and this also 2t, right? Not 2tb because the bit duration is 2tb. Okay, and then you multiply by the carrier, and here also multiply by the carrier and add these two, and you transmit, right? So this is a process we have done in MSK. Now instead of going all this process, it is a lengthy process, right? All this process. Okay, so instead of going through all this process, directly I can generate the similar spectral characteristics waveform through a process called FSK, because you have an incoming data stream, right? Incoming data stream split into two, odd streams and even streams. Then odd streams are denoted by your half cosine pulses cos pi t by 2 tb, and half sine pulses are denoted by sin pi t by 2 tb. Then multiply by the carrier. So this carrier is going to be say, let's say, cos of 2 pi ct, carrier frequency 2 pi f ct, and here the carrier is sine of 2 pi f ct, two carriers, and add it, and this is your MSK waveform. Okay, this is how we have been weaving the MSK waveform generation so far, and offset QPSK waveform. Okay, so these are the I streams, and this is the Q streams. Okay, and this is I stream is being shaped by the cosine pulse, and the Q stream is being shaped by the sine pulse, and then we are introducing the carrier, that is the cos 2 pi f ct, and here sin 2 pi f ct, and then we are adding. So this is how the offset QPSK waveform is generated, or the MSK waveform is generated. And the only difference between as I told you already, the MSK and the QPSK would be that offset QPSK would be using a rectangular pulses. Instead of this half cosinusoidal pulses, I am using rectangular pulses in QPSK. But look at here, this I bit channel and the Q bit channel both are offset by TB seconds. Okay, this is TB seconds half shift. The quadrature channel pulse is shifted by a bit duration, okay, TB. So these are mutually offset with respect to each other. So this is how we have reviewed the the MSK generation so far. But now what I am suggesting is, since we can view the frequency of the MSK waveform to be either f1 or f2. See, in MSK I said here I have f1 and here I have f2. So what I do is, instead of doing this all kind of lengthy process, what I can say is, you take the incoming data stream, let's say you have 0 1 1 0 1 1 like this. If 1 comes, you map onto 1 bit. Okay, so 1 frequency, let's say f1, and 0 comes, you map onto another frequency f2 as your choice. Therefore we could have directly generated an MSK waveform which could perhaps different from this waveform, like let me draw the figure. Okay, this waveform, the phase continues at every transition of the bit. So instead of deciding the I and Q pulse pattern, we could have directly looked at the phase function, and then we could have generated the final modulated waveform. So therefore what you do, if I'm sorry, maybe you can choose this way, or you can choose, if 0 comes you map onto F1 and 1 comes you map onto F2. And this F1 you can say 1 plus FC plus 1 over 4 TB, and F2 equal to FC minus FC minus 1 by 4 TB, or the other way around you can take it, no problem. So therefore I have a sequence of pulses 0 and 1, and this is given to FSK modulator. So what is your FSK modulator is doing? What your it is mapping 0 to 1 frequency, let's say F1, and 1 to the another frequency F2. So you have two frequencies, F1 for bit 0 and F2 for bit 1, or the other way around you can choose. So now what you do is, if F1 and F2 are selected to be the same as we discussed earlier, like F0, FC minus, no, in this manner, FC minus 1 over 4 TB and FC minus, let me delete this, FC minus 1 by 4 TB, then again you have a minimum distance or minimum shifting by 1 by 2 TB. Okay, these two are apart from 1 by 2 TB. So therefore if you just look at the waveform at every bit interval, you will find the frequency to be either FC minus 1 over 4 TB or FC plus 1 over 4 TB. So qualitatively we will not be able to make out any difference between the two waveforms, but if you look at minute level, the waveforms are different. Okay, in the sense in OQ, in MSK, what we said is, MSK what we said is, let's say you have 1011. So this is my even bit, this also even bit, this is odd bit, and this one is odd bit, right? So you separate into even and odd. So even bit is 1 and 1. Let me take one more bit here, 0, then 0, and the odd bit is 0 and 1. Now what you do is, here you take cosinusoidal pulses like this, and again cosinusoidal pulses like this, half cosinusoidal pulses like this, you have the pulses like this. So this is for 1, and this is for 1, and this is for 0. This is minus t by 2 plus t by 2, and so on and so forth. And here what you do, you shift by tb seconds apart, okay, to the right, delay by t by 2, delay by tb seconds in Q channel. Therefore you have the pulse like this, this is 0, and this is tb by 2, this is tb by 2, then you have 1 like this, this point is tb by 2, is it tb by 2? No, it is tb, I'm sorry. It is tb, and it is 2 tb, and so on and so forth. And this again you modulate with this is cos of 2 pi f naught t, and here you modulate by multiply by sine of 2 pi f theta, and add these two things together, and you get the modulated waveform. Okay, modulated waveform. Now let's say the modulated waveform like this, and here you may have some cycles, and here you may have some cycles, and here you may have some cycles like this. Now I will take the same sequence here. What is the incoming sequence here? 1 0 1 1 0. You take 1 0 1 1 0. Now what you do? This is your MSK waveform, and if you look at the FSK waveform. So in the first interval you have one frequency for 1, and in the second bit interval this is for 0 and this is for 1, and again for 1 and again for 1. I am drawing this figure very roughly, please forgive me. And again this is for 0. So if you look at bit by bit basis, they are different, they are not same. Okay, if you look at from from this bit interval to this bit interval, whatever the frequencies you are having in this interval, let's say this is frequency f1, you may not have the same cycles here, but this is interpreted as an FSK. Okay, but if you look at minute level or in a spectral level, it may not be the same, it cannot be, it will not be the same. Okay, so this is different from this one. So let's say here f2 and here I have some other frequency, and this bit interval whatever I have, this may not be the same as this one. Therefore what I'm trying to say is this, the MSK waveform can be viewed as an FSK, but they are not the similar. So you cannot use the decoder or demodulator which you are using for MSK to decode for an FSK. So what are the demodulator which you are using for MSK, that you cannot use it for FSK demodulation. Similarly, the demodulator which you are designed and used for FSK, which cannot be used for demodulating the MSK waveform. So that is a key point which we need to understand in this. Okay, therefore what we say is corresponding to 0 we have a higher frequency. In general what we do is corresponding to 0 we choose higher frequency, that is Fc plus 1 by 4 TB, and corresponding to 1 we choose lower frequency, let's say Fc minus 1 over 4 TB, 1 upon 4 TB, just for the sake of argument. That means for every incoming 0 I could choose a higher frequency. If 0 comes, I choose higher frequency, and 1 comes, I choose lower frequency. If I choose higher frequency, what do I mean? Increase the phase. The phase is increasing. And if I choose lower frequency, the phase is decreasing. Therefore, the behavior can be well described by something called phase diagram. So that I can draw like this. Let's say if 0 comes, then you increase the frequency linearly up to pi by 2. Then in the first let's say like this, this is TB, and then in the first bit interval 0 comes, and the second bit interval 1 comes, then decrease by pi by 2. Then in the third bit interval also 1 comes, again decrease pi by 2. This is minus pi by 2. And in the fourth bit interval also, let's say again you are getting 1, again decrease by pi by 2. This is minus pi. Let me in the fourth bit interval I am having 0, so you increase. So at this point, let me delete this. You reach this point. Oh my god. So that means you reach this point, minus pi by 2. Again, if you have another 0 in this bit interval, you slowly reach here 0 phase. So like this your phase will travel from 0 to pi by 2, then pi from this point to 0 minus pi. Because 1 comes, you are choosing lower frequency, that means you are decreasing the phase, gradually decreasing. Note here the phase is changing linearly, okay, changing gradually. Gradually or linearly it is changing. So over the bit duration. So note the phase is changing linearly or gradually, okay, over the bit interval. So this is an important point that we need to remember in MSK. That is why this is very popular in digital communication systems, because it gives the constant envelope signal. Therefore, the MSK waveform can be interpreted as an FSK waveform. But if you look at bit by bit basis, bit by bit interval basis, the waveforms are not similar. So that is very important point. Not. If you look at bit by bit basis or bit interval by bit interval basis, the waveforms are not similar. Similar between FSK and MSK. That means what are the demodulator that you design for your FSK which cannot be used for MSK to demodulate the MSK waveform. Similarly, the demodulating circuit which you designed for MSK which cannot be used to demodulate the FSK waveforms. Okay, so these are the important points that we need to remember. So in this lecture we have seen how we can interpret the MSK digital modulation scheme as an FSK digital modulation scheme or digital modulated waveform. Okay, so because every bit interval we are choosing either one of these two frequencies, either f0 plus 1 over 4 dB or f0 minus 1 over 4 dB. So therefore we can interpret or we can view this as a FSK frequency shift keying. But of course in FSK we use orthogonal frequencies, both are perpendicular to each other. And the minimum separation between these two frequencies should be 1 over 2 TB, where TB is the duration of the your waveform. If you use the carrier of sine omega 1t and another waveform sine omega 2t, where omega 1 is equal to 2 pi f1 and omega 2 I can write 2 pi f2, and where f1 equal to let's say fc plus let's say minus 1 over 4 TB, and f2 equal to fc plus 1 over 4 TB. And if these two guys are orthogonal, in order to be orthogonal, or if you want orthogonality between sine omega t 1 sine omega 1t and sine omega 2t, the minimum frequency separation f2 minus f1 or modulus of f1 minus 2, whichever you like it, it is going to be 1 over 2 TB. And this signal exists from, it is not infinite duration signal, that point you should remember. And this also the duration is t 0 to t sub b. Note sine omega 1t and sine omega 2t both are finite duration signals. Finite duration signals, meaning the signal duration is from 0 to TB. That's it. So that's all about the interpretation of your MSK as an FSK digital modulation scheme. And at this point I would like to stop this lecture. In the next class we will see the M-array passband digital modulation schemes. Thank you very much.